then. That's the plan for this unit. Okay, ethers. Next chapter is all about ethers. Can somebody tell me what's an ether linkage?
ROR.
So an ether family is some R single bond to O and then R again on the other side. Now those R's can either be the same, those are called symmetrical ethers. Symmetrical meaning that both sides are the same, so that means R and R prime are the same. Or they are unsymmetrical ethers, which basically means those are different organic groups. So when R and R prime are not equal to each other, those are called unsymmetrical ethers. Okay, so naming of ethers. Again, there's a common system of naming and then there's the IUPAC system of naming. In the common system of naming, which only works for small, uncomplicated ethers, the common system works. So basically, if you have an ether, whatever the alkyl is, followed by an alkyl, another word, and then the word ether. So there are three words, three separate words. Of course, these are in alphabetical order, as you would expect, because it's really, that's how we name things, right, in alphabetical order. So three words, alkyl, alkyl, ether, whatever those alkyls are. But if it's a symmetrical ether, which means the alkyls are the same, then it's simply dialkyl ether. So those are the common names for ethers, and it only works for small ethers, simple ethers. So for example, how would you name this guy? Common names, just the common names. So, common names, not IUPAC yet. What would be the common name for this ether?
Dimethyl ether.
Do you all agree? Because it's a symmetrical ether, the two R's are methyls, hence dimethyl, and then followed by the word ether. Yeah. How about the next one?
Methylpropyl ether.
No. That's an ethyl group.
Oh, methyl.
That's a methyl group. But what comes first alphabetically?
Ethyl methyl
Ethyl.
ether.
So in alphabetical order, ethyl comes first, then comes the word methyl, and then comes the word ether. Please note there are three separate words. Okay, next one. Hey, Mark.
Oh, yes.
Please, thank you. What about the next one?
Benzophenyl ether.
Could you say that again, Dash?
Benzophenyl ether.
Exactly. This is a benzyl group, this is a phenyl group, and the word ether. Absolutely. So in alphabetical order, benzyl, phenyl, ether. Next one,
Diphenyl ether.
diphenyl ether, because they're both the same group. And the last one. So,
Is this where it gets difficult?
no. Well, you actually not so much. Now, you may not have seen, well, you kind of have seen it before, but not formally. Does anybody know what's the common name for this group? This is a vinyl group. Because the attachment is on the carbon, made up of two carbons, that's a vinyl group. And this one, any guesses? Louder? Exactly. That's the allylic position, so that's the allyl group. That's the vinylic position, so that's called the vinyl group. So when you're naming it, how would you name it then?
Allyl vinyl ether.
Allyl vinyl ether. Again, those are common names. Those are not IUPAC names. But our common names only work for simple ethers. You cannot use common names when ethers get a little bit more complex. For example, that, yeah, we can use it, name it differently as well. But any questions about common names? Okay. According to the IUPAC system, ethers are not named as ethers actually. Ethers are named as alkanes or alkenes or alkynes with the ether group. This group, OR group, is called an alkoxy group. And you've seen it before, actually, you've done it also a couple of times without us calling it an ether because ethers is not named as ethers in IUPACs. For example, let me give you an example and I think it will make more sense as to what I'm trying to say. It's an ether. If you think about it, it's an ether. Isn't that right? Right there. But we don't name it as an ether. What's the parent here? Hexene. It's actually an alkene because the ether group does not get priority. It is not considered as the parent. It is actually the group. The parent becomes the longest continuous chain, either an alkane or an alkene or an alkyne or an alcohol, whatever the long parent is. Ether is just a group. That's just the group. Everybody okay? So how do we name this stuff? Because we've done this before. So what do you think will be the name for this guy? Absolutely, that's the parent. Okay. Period. This is not the parent.
Two.
So that's
would it be 4-alkoxyl?
so what is not alkoxy? It's alkoxy. But what's the alk part?
Alphoxy.
It is F-oxy. F for the two carbons, oxy, because it's an ether group. Do you guys see that, everybody? So the alk is the number of carbons in the group. So that's F and then oxy. But who comes first, ethoxy or methyl?
Alphoxy.
So let's name this.
It's 4-epoxy, 5-methyl, hex 2.
Methyl what?
Hex 2
1,
E.
2, 3, 4, 5, 6. Hex. Oh, what am I doing? Why do I have two H's there? Hex 2E. Everybody okay?
Yep.
What's missing? Because you lost a point right now. You got to do stereochemistry. I don't know why we don't do that. You got to remember, if stereochemistry is visible, you have to include it, period. It is E in this case. You have to include the stereochemistry if it is visible. So that is, so the point I'm trying to make is that the alkoxy group, the ether group, is not the parent. The parent is the rest, as we've already learned. The group is an alkoxy group. Make sense, everybody? Yes, you want to name a few more?
Yes.
Sure.
Okay, because we don't have a choice. I make it seem like you have a choice. Actually, don't. Okay. It's always about the illusion, right? Yeah. Okay, so let's try a few things. So the parent is not the ether. The smaller ether group is the group. The parent is whatever the else is, whether it's an alkane or an alkene or an alkyne or an alcohol, they are the parent, like we've already learned. So let's give this a try. What would you call this guy?
4-bromo, 5-methoxy, cyclopentanol.
Do you all agree? Everybody agrees?
Yeah, I think I have to.
What did they say? Anyways, what do you think it should be?
Cycloheptanol.
Do you all agree? So the parent is again the alcohol. This is not the parent. So you have to start numbering from there because it's a cyclic system. And then find the smallest combination. Everybody okay with that? Questions?
Question.
Yes.
Why bromo first?
Because alphabetical. So if you did it.
No, not alphabet, but why that way, not that way?
Good. So let's try the other way. So if we had gone the other way, 1, 2, 3, 4, 5, 6, 7. Agreed?
Mhm.
So what would be the number for bromo?
5,
And what would be the number for methoxy?
4.
So the point
Oh, I
is,
see, because then it comes first, okay.
exactly.
All right.
First is lowest combination. If the combination is the same, then alphabetically smaller gets, right? Absolutely. Okay, next one. What's the name for the next? So what's the parent in the next one? Anybody?
1, 2, 3.
Guys, come on, let's not take it so long.
Hexine.
It's an alkyne, exactly. Is it hex?
Hexine.
Which
Yeah.
direction did we go? 1, 2, 3, 4, 5, 6? Or
Yeah.
1, 2, 3, 4, 5, 6?
No, the
First
other.
one.
Right? More branches. If you
More
have
branches.
2 chains of the same size, then the more branches is the correct parent. And then what's the highest priority group in that?
Alkyne.
So it has to get the smallest position number. Do you all agree?
Mm-hmm.
Everybody? Okay? Okay. Please tell me what the name should be. Is there any stereochemistry shown for us to include?
No.
No. If it's shown, you must. If it's not shown, you don't. You don't. Okay. So which group's going to come first?
6
Epoxy, not ethoxyl. It's just ethox. You got to practice that. It's not ethoxyl. It's epoxy.
What's the difference between?
It's like, my name is Sumita. My name is not Sumita. Whatever. That was so very weird. I don't know where I was going with that thought. I was going somewhere. I just lost my way. The point is that's what it is. Okay. Coming back though, let's name this. So who's going to come first? Ethoxy. See, this is ethoxy. What is this?
Phenyl.
And this?
Ethyl.
So alphabetically, which one comes first? Do you all agree?
Epoxy.
Okay. Who comes next? Or what comes next?
Ethyl.
So that is at?
4.
Then comes what? Phenyl. At?
6.
And now the parent. What's the parent?
Hexine.
Hex.
2
3.
2.
I mean 2.
Ine. The naming always, the position of the group is always the smaller, not the larger number. The alkyne started on carbon 2, not carbon 3. So it's not 3-ine, it's 2-ine. Everybody okay? Any questions? Okay, last one, please. What's the parent? Can I raise these two? What's the parent? Sorry. Heptane, you said? Okay. Did you have a question, Camilla? I thought your hand was raised.
Oh, no.
Okay. So, is there stereochemistry?
Yeah.
So let's first take care of that. First thing is stereochem. Let's take care of that first. So is this going to be EZ or RS?
RS.
Okay. What is this one? R or S?
R.
I think it's S.
Is the ether included in the parent chain in this one?
No. No. So that's a group. This is a group.
That's
So
an
the
R.
parent is 1,
Hex.
2,
Hex.
3.
Heptane.
Wait, does color oxygen?
You got to go. I think this is what a lot of you do. When you're doing RRS, you got to do layer by layer. Don't jump the layers.
Yeah, so it'd be R.
So maybe I did it wrong. Priority 1, agreed?
Yep.
Uh-huh.
And the H is priority 4.
Yes.
Get it out. Okay, now let's go layer by layer.
Okay.
Carbon, carbon, same. Isn't that right?
Yes.
Yep.
What's the second layer?
Carbon.
Carbon.
What is carbon and hydrogen? Hydrogen. Chlorine is the third layer. Second layer is CHH. Agreed?
Uh-huh.
What's the second layer here?
C's.
Carbon, carbon, carbon. So who takes priority? That side takes priority. Isn't that right?
Uh-huh.
Oh.
So you got to go layer by layer. Chlorine is the third layer if we needed to go to it. Right now we don't need to go to it. So do you agree? Priority 1,
Yep.
priority 2,
Mhm.
priority 3. So is that R or S?
S.
Exactly.
Because you're going in the opposite direction.
So please be careful. Don't jump the layers. You got to take it layer at a time. Okay, let's start with groups now. Who's going to come first?
7 chloro.
7 chloro. So why did we start numbering from here and not from there?
It would be 1 chloro.
Lowest combination, right? So start from the end closest to the first group. The end that is closest to the first group is this end.
So 1 chloro.
1 chloro. What comes next?
Is it T-butox?
Exactly.
Okay.
Third butoxy, T-butoxy, either way. Does that come next? Yeah, B versus E over there. So what is it? 3? T doesn't count. Remember, TERT doesn't count. Iso and cyclo are the only two prefixes that
That's
count for alphabetization. No other prefixes matter.
So T-butoxy.
So T-butoxy, now you can
T-butox.
either write it as T-butoxy or you can write it as TERT butoxy. I mean, that's totally fine.
Shouldn't that one be first though?
Yes, thank you so much. Totally, yes, absolutely. C comes after B. B comes before
Got
C.
my alphabet messed up.
Yeah, constantly. Yes, you're right. Butoxy should come before chloro. And then what? After that comes what? 5-ethyl. Then comes what?
4,4-dimethyl.
And
Heptane.
so the point is the ether is not the parent. It's only a group, just like other groups. It just gets counted like other groups, alphabetized like other groups. Really doesn't matter. Everybody okay? So it should be S, 3 third butoxy, 1 chloro, 5-ethyl, 4,4-dimethyl heptane.
Mm-hmm.
Questions?
Oh, and did we have to write down like free S to indicate?
If it's only one stereo center, the 3 is redundant. It's not
Oh.
very useful information. But if you were to, it's not wrong. It's just not necessary. But if there is more than one stereo center, then you must say which one is R or which one is S and so on and so forth. Yeah? Yes, Carrie?
If the ethyl was next to a benzyl or phenyl, what would you need? Would it be
What do you mean?
Phenoxy or
I'm not sure I... Say that
So
again.
instead of the T-butyl group,
Uh-huh.
there was a benzene ring.
Oh, I see. So just randomly, whatever.
Yeah.
And you're saying if it were a benzyl ether?
Yeah, what would be the name of that? Benzoxin? Benzox. Okay.
Yeah.
Or it would be.
So the L is not here. It's not that.
Yeah.
But if this were, let's say, whatever phenol, then that is phenyloxy. Anything else, guys? Of course, ethers can take a lot of different forms. We are not getting into all of those, but this is the simpler versions of ether, that ether is not the parent. The parent is either the longest alkane or the alkene or the alkyne or the alcohol. The ether is just a group like all other groups. It actually has a very low priority, just like other groups. Are we okay, everybody? Yes? Okay, how do we make an ether? Now, there are two ways of making an ether. One that you know, second one you kind of sort of know. Can you guys tell me one method of making an ether that we have studied so far? Last week, actually.
Williamson's ether synthesis.
Exactly. One of the most common ways of making an ether is Williamson's ether synthesis. What does that synthesis start from? With, rather.
RO negative.
Where does the RO negative come from?
An alcohol.
So, it's an alcohol that is deprotonated to become an alkoxide ion. Guys, do you understand alkoxy versus alkoxide? IDE means it's an anion. Alkoxy means it's a group covalently bonded to whatever else. There's a difference in our vocabulary. So alcohol is converted into an alkoxide ion. What do we need to do that with?
Sodium or lithium.
Okay?
Sodium hydride.
So either sodium or lithium or sodium hydride or.
Sodium amide.
So the point is, we can't just use a normal base. We need something very strong to deprotonate a weak acid into its conjugate base. Everybody okay? And then what is the alkoxide reacted with? Come on guys, this was last week.
RX.
So,
Or a
and that
alkyl
gives
halide.
us,
RO.
right? What's the mechanism of this second step?
SN2.
So if it's SN2, what must be, what must be the structure of R prime? If the second step is SN2, that puts a restriction on us. It has to be unhindered.
It has to be
And
an
yes,
unhindered
primary
RX.
is the best. Maybe secondary, but never tertiary. Absolutely, because you want to do an SN2 reaction, which means the electrophile has to be unhindered. Does that make sense, everyone? So, how? Will I make this using Williamson's ether synthesis? What would you start with?
Do you want us to go up or?
Sure, yeah. Give me just 1 second. Yeah, please, absolutely.
We could start with phenol.
Let's write it. Let's write it on the board.
Okay.
I think Dash is doing the first one. You can do the second one if you'd like to. You don't like the long arrow?
Well,
I'm
I
just
need a
kidding.
little bit lower
I'm
space
just
here.
joking. Oh, I see. You're going to write that. Okay. Okay. That's fine. No, good, good, good. Yeah, yeah. That's fine. Yes,
Is using a Grignard completely different?
totally different.
Okay.
Grignard does not make ethers at all. Makes alcohols.
Okay.
Do you guys agree with this? Now, here's a point though that I want to ask you. Why did we make this the alcohol and this the electrophile? Could we have, could we have made this
No.
the alcohol? In other words, could I have done this alcohol deprotonated O minus using, and then used to make the same ether?
Hold on.
Why not?
Because SN2.
So?
It's hindered.
Who's hindered?
Phenyl
PHBr.
bromide.
Is it really just hindered?
You can't do.
It's actually not hindered, but you're absolutely right. This is the wrong thing to do. But why? Go ahead.
BR can't be a leaving group on, because it's sp2 hybridized, not a benzene.
Exactly. SN2 does not happen on sp2 hybridized carbons. SN2 happens on sp3 hybridized carbons that are unhindered. So it has to be sp3 and unhindered. It cannot, this not right. Everybody okay? Just one quick reminder, everyone. Phenol is way more acidic than alcohol. So we really don't need this with phenol. Phenol having a pKa of about 9, it's more acidic than other alcohols. Sodium hydroxide is good for phenol because it is actually quite acidic. So you don't need something as strong as that. Sodium hydroxide is good to deprotonate, do SN2, give the ether. What about this one?
Yeah.
Jasmine, you're almost off your chair. You might as well stand. You were like,
Got this,
"How?"
Jasmine.
Just go.
Yeah, hold on. Is that how you want me to do it?
No, that's fine. What you did was good. Cool. So why did you decide to, once again, the same question is, why did you decide that this is going to be the alcohol and that's going to be the electrophile?
Because it can't be an sp.
Well, they're all sp3.
They're all SP3, but
It would be hindered.
What will be hindered?
The.
You don't want this carbon, you want this carbon to be unhindered sp3. Exactly. This carbon where the sp2 is happening. We don't want that carbon, this one, to be available for SN2 reaction. So you have to make sure that one is not hindered. Is everybody following that? Everybody okay? It's the second step, that's SN2. So you got to make sure that your substrate is unhindered sp3 hybridized. So the rest comes from the alcohol. Everybody okay? What? Mark?
OH.
OH where?
There.
Alcohol.
Isn't it? Oh.
Yeah. Isn't OH an alcohol?
Yeah. I thought it was the alkoxide.
Yeah. Isn't that what's going to be created first?
Oh,
Yes.
okay.
Number one.
And then you put
And then
the
that reacts here, step number 2.
Oh, okay.
It's a 2-step process. Step number 1 makes the alcohol into an alkoxide,
Oh,
and then that reacts to give. So it's step 2 that is SN2. Make sense?
Yes.
Everybody okay? This is the most common way of making an ether, but there is another method. We've already done this last week, so let's go to the second way of making an ether, which is also somewhat common. Not as common as that though, but do you guys remember this reaction? Alkoxymercuration, demercuration,
Yes.
right? Do you guys remember that?
That's only W, was it?
Sorry, no, oxymercuration.
Oh, yeah, that's what I thought.
Sorry, oxymercuration.
And demer.
Now this is alkoxymercuration. No. And what's the starting material for oxymercuration, demercuration? What do we start with? No, the reactant, the starting material. Oh.
I think we start with an alkene.
An alkene. So, An alkene, let's use a specific example. An alkene. Do you guys remember this? Please tell me if you remember. HgOAC
Mercury,
twice with water
mercury 2 acetate.
and sodium borohydride in a basic environment in the second step. Do you guys remember?
Yeah.
What's the expected product from what you remember?
Markovnikov's
No, Markovnikov's what?
without rearrangement.
What? What is the product though? Markovnikov without rearrangement, what?
Alcohol.
Alcohol. Alcohol. So what would that be in this case? Because we know how to name alcohol, so what would that be in this case?
2-methyl cyclopentanol.
Why would it be 2?
Oh, 1-methyl?
Don't we want Markovnikov? So isn't that the Markovnikov position? That's the anti-Markovnikov position?
So 1 methyl.
Make sense? So 1-methyl cyclo, isn't that right? Everybody?
Yes.
Do you all agree with that? And yes, we don't need to know the mechanism for that. Now, that is oxymercuration, demercuration. We are doing alkoxymercuration, demercuration, which means if one of those H is an alcohol. Isn't that an alcohol?
Yes.
If you take one H on water, replace it with R, that's an alcohol. So instead of using water, if we use alcohol in the first step, what will be there?
An ether group.
That's an ether. It's exactly the same reaction as oxymercuration, demercuration. The only difference is that in the first step, instead of using water, we are using an alcohol. So therefore the product is ether. It's still Markovnikov, it is still without rearrangement because there's no carbocation in the mechanism, but you get an ether. Hence alkoxymercuration, demercuration. Does that make sense, everybody? Yes? Okay. Please tell me what would be the outcome.
What's the arrow doing? Is it pointing?
Where is it starting from?
The
It's
product
starting
from the
from
first.
here
Product
and
from.
it's going there.
Okay, I thought it was taking a step
That would
3
have
of
been,
the.
yeah, that was fine. Let's clarify it. Yes, exactly. Please, let's go ahead. Let's try and figure this out. Someone other than Dash. I'm just kidding.
You'll get
Next time, someone other than Dash. Dash is
Dash is brave.
brave.
It's smart.
Oh, you just stopped there? You didn't take it all the way? Okay. Okay, no, that's fine, that's okay.
Wait. H2. H2.
Okay, let's see. So, NBS, what does NBS do?
We are
MBS adds a
we
bromine.
are in
To
the
Adds a bromine
benzylic position.
in the
Agreed?
most stable.
position.
Do I need to draw this or we guys got it?
Got it.
We got it.
Okay, so what is step number 2 doing?
Reading alcohol.
E2, making an alkene because that's the only option. Everybody okay?
Yep,
Yeah.
And then what is step number 3 doing?
it makes a primary bromide.
Because
An-
that does anti-Markov.
Anti-Markov.
Everybody okay giving us
bromination.
this? Counter carbons. Please make sure you're counting carbons. Everybody okay till that step?
Yes.
Yep,
So what I'm suggesting is, once you get this, that comes here as step number 2. So what is step number 1 doing? Oh, you did that, okay.
step number 1 adds an alkene to the
No.
No.
No. Step number 1 is deprotonating one of these terminal,
Deprotonating.
right?
Yeah.
acetylene.
And then that becomes a nucleophile, does an SN2 to create this. Everybody okay?
Yep,
1, 2, 1, 2. Now, step number 3 is doing what?
reducing it to an alkene.
Alkene, exactly. 1, 2, 3, 4, 1, 2, 3, 4. Everybody okay?
Mhm.
Does it matter whether the alkene or E or Z? In this case,
Not
can
in
we
this
have-
case.
It can't be E or Z, right? So it doesn't matter what we used here because you'll get the same alkene.
Could we put Ni instead of Linders?
Ni?
Yeah.
Where?
NH2Ni? No.
No, that's Lindler's catalyst. If you did hydrogen with nickel or palladium platinum, that will over-reduce this and it'll become an alkane.
Oh.
It's Lindler's catalyst, which is the poisoned catalyst, which means it stops at the alkene, it doesn't go further.
Oh, okay.
So you gotta be careful.
Okay.
Everybody okay with that? And now we have an alkene, so combination of 4 and 5 gives us the Markov-Nikov ether. Everybody okay? Cool, let's try that one. Please. Questions, any question on anything? Now do you see, guys, again, you just, it's the ability to pick and choose what you need in order to achieve what you need to achieve is what we need to get to.
You can
And
try. What can you guys?
that's, and you
If
can
I'm wrong.
write anything and just
Okay,
take
no,
it.
no, don't go there.
Take it where it goes. See where it takes you.
Hmm?
As long as you go through it step by step.
I don't know if I know the right answer though.
I don't know either. I just made stuff up. So let's see where it takes us.
I
I'm
can
trying to-
try, but I'm not
Please,
sure.
I can help
Absolutely.
you at least. The part
Yeah,
of the
'cause-
first one is gonna be.
Okay, everybody just say yes now.
And everybody will help. Yeah. And I'm also hoping that, because I was trying to picture it in my head, so hopefully I got it right too.
Yes, no. Yes or no?
Yes,
Yeah, that's right.
because that's a more stable radical, free radical, or it's from the more stable free radical.
No, I don't know what it is.
It doesn't.
Zaitsev, because it's a non-bulky base, so you'll get the Zaitsev's alkene. Okay.
Okay.
We're gonna watch Dora the Explorer right now.
Huh?
So we're gonna watch Dora the Explorer right now.
Is that how she does? I don't know.
Where's the barn?
Okay.
And the VR.
Is that Markov-Nikov or not? No.
It goes to the dumbest spot it can without removing. Yeah.
It's the alkene that is reacting. Okay, now what?
Now this is boogie.
Isn't step 3 a peroxide?
No. It's anti-Markov-Nikov hydrobromination. It goes through a free radical mechanism, but the product is not a peroxide. The product is what Mar has on the board.
Okay, yeah. But isn't it a primary bromide?
Not in that case. Where's the double bond?
Oh, there we go.
The
Thank you.
double bond cutter. Exactly. So see how you shifted the position of the double bond. You went from that double bond to this. You're able to shift where it's going to be. Okay, now we can. Okay. And then, yes,
Oh. Oh, okay. MG, that's it?
that's it. Okay, so now that's on the top.
What? Now what?
You can draw this here.
Oh,
That's what you get after step 6, right? After step 6, that's what you're getting. You're getting a Grignard reagent. Okay, now the Grignard reagent is reacting with the ketone and so on and so forth. So maybe, how about if we just, because it's right here. Is everybody okay so far? Now you're taking that Grignard reagent and making it go through 1, 2, 3, 4, 5. What are we going to get?
Like, oh, yeah. Counter cup. Link.
Not here.
No.
No, that's not a carbon.
No.
Mar, that's
Oh,
not,
no, this is not a cup.
that's going to magnesium. Okay?
Oh, well, can I just?
Yeah, you
put an
can,
H?
absolutely, absolutely, there we go. So that's after, okay, good. Then, step number 3.
Yes.
There's no carbon there. You just added
Oh,
a
that's
carbon.
right. So keep it?
No, that's not what I said.
It's a dehydration.
It's a dehydration, good. Zaitsevs or Hoffman?
Huffman.
No.
No.
Zaitsevs.
Oh, Zaitsevs.
Alcohols are always Zaitsevs. There's no possibility of making Hoffman with alcohol dehydration. So where would the double bond be? Yes, but you're missing something.
Yeah, I'm missing a lot here.
Yeah, you're right, except you can maybe draw it better.
Yeah.
But you're fine. Okay, go on. So now what about 4 and 5?
And, oh, wait, 4?
Oh, shoot.
Are we missing something?
You see it, right? Yeah. No, not you. I'm missing something. But that's okay. Yeah.
Because then we're trying to convert an alcohol to
Wait,
ether. Or no,
This is reducing or the mercuration? No.
that's the alkoxy mercuration,
Oh, and I
demercuration that we went over
Okay, I'm
just
stuck here.
a while ago.
Anybody?
Um,
Steps 4 and 5. 4 and 5.
Remind me,
This is alkoxy mercuration, demercuration.
so we make an alcohol here.
No, but not an alcohol this time because we are adding an alcohol. So that's going to make an ether.
Oh.
Instead of HOH, we are adding ROH.
Okay.
But goes
I
Markovnikov or
don't know where to add it though.
and that's
Anybody
my
else?
mistake. That's not your mistake.
Anybody else?
Does it go Markovnikov or anti-Markovnikov? Good job.
Markov.
Markovnikov. But the mistake that I have is one carbon better than the other? No, they're both di-substituted, right? They both have 2 R's. So is there any selectivity in this case?
No.
Not really. So how many products would we get?
2.
We'll actually get 2 because there is no selectivity. 1, 2, 3.
So they be equal?
Second?
Would they be equal?
I would assume so. Yes. So and 1, 2, 3, 4. 1, 2, 3, 4. That and because there is no selectivity, unfortunately, yes, we will get both. 1, 2, 3, 4. But That's the step where the ether is being created on the Markovnikov ether on the double bond.
Oh.
But yes, in this case, there was no selectivity because both carbons are kind of the same. So I guess you draw both. But does everybody see that?
Mm-hmm.
Okay, cool. So two different ways of making an ether. Williamson's ether synthesis and alkoxy mercuration demercuration. Questions? Okay, reactions of ether. Can I erase this, everything? Everybody okay?
Yep.
Now, one of the most common purposes of ethers is to behave as a solvent. Can someone tell me what's the role of a solvent? What is a solvent? Louder? Dissolves. So
dissolves the
what's
solid.
the role of a solvent is to dissolve everything so everything is in one homogeneous layer. Isn't that right?
Yep.
So what's the quality of a solvent? What's a good quality of a solvent? Anybody?
Liquid.
Well, that's not necessary. Depends on what you want to do. But generally speaking, when you're selecting a solvent, what do you want it to be? What do you want it to achieve? And how do you select a good solvent? Like dissolves like, so you want to match polarities and all of that
Yeah.
stuff. What else?
That is
What else
the
is
density, like that is not too, no.
Density does not factor in unless you want to do extraction where the position of the layer matters. What else is a good quality of a solvent?
You don't want it to react chemically.
In most cases, of course, sometimes we want it, that's a separate issue, but in most cases, we don't want the solvent to react with the things that it's dissolving. In some cases, yes, that's solvolysis, that's one exception, but in most cases, we don't want solvents to be reacting with what they're dissolving. So ethers are very good solvents because ethers are unreactive in most conditions. Ethers are totally unreactive, do not react, are totally immune to, inert in basic conditions, oxidative conditions, or reduction conditions. They do not react at all. They're totally unreactive in those conditions, except, what am I missing here?
Acidic.
Except acidic conditions. That is why we probably don't want to have ethers under acidic conditions, because under acidic conditions, yes, they will react. So, and this is something you've seen, by the way. You've seen it before. Let's say that's an ether, agreed?
Mm-hmm.
And we have an acidic conditions like HX. So when I say acidic conditions, actually it's specifically for HX. It can't survive. What do you think will happen first? Let's walk through the mechanism. If you're seeing an ether like that and there's HCl, which is an acid, what would your brain tell you that, oh, that's going to happen first? Come on, guys, is this an acid or a base?
Acid.
So is there a base around in the system?
In
You've done it.
the
You've done it
ether?
before.
Yes.
Please don't say no.
The oxygen.
Haven't you protonated an alcohol before?
Yes.
Haven't you protonated water before? How is that oxygen any different? It's also an sp3 hybridized oxygen with a bent shape and two lone pairs. How is there any difference between this and any, let's say, an alcohol or H2 or whatever? If I were to do this, would you wince? You've done it thousands of times. Isn't that right? So why can't that happen? The answer is absolutely it can happen. Everybody agrees?
Mm-hmm.
Now here's the problem though, when that happens, what does that become? Louder please.
On the oxygen side.
Yes, absolutely. And what does that make this piece become? Have you seen this before? If I were to do this, how many of
Good
you
leaving
will,
group?
how many of you will nod your head?
What makes it a good leaving group?
Good
And what
leaving.
does it become?
A good leaving group.
So why can't that be a good leaving group for exactly the same reason? But which one? Right? The point is it this one that's a good leaving group or is it this one that's a good leaving group? The answer is both.
Mm-hmm.
But one at a time, not together. One at a time. What do good leaving groups do? What kind of reactions do good leaving groups want to go through?
So
Substitution.
substitution.
SN1 or SN2? Well, that depends. That depends on the substrate.
Mm-hmm.
So if do I have a nucleophile in this system?
Chloride.
So if the chloride nucleophile attacks this carbon, would that be SN1 or SN2?
SN2,
And why would that be SN2?
because there's no problem.
Concerted.
Because that's primary.
Oh.
That would be SN2. If it's SN2, can you write a transition state?
Yes.
Please do. I'm not. Please do. And then when the transition state goes through, what does it become? What does this piece become?
It becomes.
What does this piece become?
It becomes an alcohol. The good leaving group.
This piece where the substitution actually happened.
An alkyl halide.
Which one? Be very specific though. You're right, alkyl halide, but which one? Anybody?
Pri-
If the chloride attacked here, kicked out the leaving group, what does this become? Where's the confusion?
Oh,
Product, it's SN2. There's no carbocation in it, it's the 2.
I thought we were doing
It's a chlor.
Chloropropane. Exactly. You got a 3 carbon with a chlorine.
Mm-hmm.
Agreed?
Yep.
That's become this chloropropane. And what about the rest of it? What does the rest of it become? The part that was kicked out, what does that become?
Ethanol.
Ethanol, absolutely. Agreed? Everybody? Can the ethanol react further? The answer is yes.
Yep.
Why not? Same way. In fact, we have seen this mechanism quite a few times earlier in the quarter. What does that become? A good leaving group. What does that do?
Reacts with the Cl minus.
To which mechanism?
SN2
So please
once
make
again.
sure you are drawing the transition state. And what's the outcome of that step?
Ethyl chloride plus water.
It's a dehydration reaction, kinda, sorta, without making an alkene. The point is, this part has become an alkyl halide, and the other part has also become an alkyl halide, as long as it can go through SN2 or SN1. Of course, SN1 is also possible, but does that make sense, everybody? So both sides, they're cleaving off, and this becomes H2O. Everybody okay?
Mm-hmm.
Let's try this again. So this is basically breaking the ether molecule into 2 parts because of that acid in the system, which protonates the oxygen, makes it a good leaving group. What will be the outcome? And let's write a mechanism. Let's do this faster, guys. As I said, we should finish this chapter today. So what will be the products? Can this piece do substitution?
Yeah. No, it can, wait.
Can this piece do substitution? I said substitution, I did not say SN2. I said substitution. Can it do SN2 or SN1?
Yes.
So what would be the product if it did? What would that piece become?
Tert butyl chloride.
You mean bromide though?
Oh, tert-butyl
Because I'm
bromide.
using HBr.
Okay, tert-butyl bromide.
Okay, what about the other piece? Can this piece do substitution, SN1 or SN2?
Yes.
So what would that become?
Benzyl bromide.
Do you all agree? And of course, there's water. Agreed? And notice we are using excess so that they both can react. Let's write a mechanism, please. First step, what would that be?
But one of the sides becomes a good leaving group.
Not yet. So, okay, sorry. How? How does one of the sides, what needs to happen for one of the sides to become a good leaving group?
The oxygen takes the proton.
Oxygen takes a proton.
Now, will SN1 happen first or SN2 happen first? We can't say. We cannot say. You can show either of them to happen first. Totally okay. Everybody okay?
Mm-hmm.
What do you guys want to do first? SN1 or SN2?
SN1.
Okay, so
SN1.
which side will go through SN1? The T-butyl side or the benzyl side?
T-butyl side.
So, let's think about SN1. So what should happen for SN1?
So, the bond between the T-butyl carbon and the oxygen breaks, and the T-butyl is a carbocation.
Makes a carbocation. SN1 goes through a carbocation. And what does the other thing become? It becomes an alcohol. Agreed? Everybody? So what is this going to do? The carbocation?
It's gonna,
Take,
it's gonna react with the Cl minus.
Br.
it reacts,
In this case,
it
but
reacts
the
with the
nucleophile-
nucleophile.
It's very traditional SN1, no difference at all. Same thing, nucleophile attacks. Everybody okay with SN1?
Mm-hmm.
Okay, what about the other guy, benzyl alcohol? Will it go through SN1 or SN2?
SN2.
Actually, it can do both because, and you've done this in the lab, by the way.
It's a benzylic.
It's primary and it's benzylic. It's primary, so it can do SN2, and it's benzylic, so carbocation is pretty stable. It can do SN1. So which one should you show? Either. Either, because it can do both. Make sense?
Mhm.
Everybody see that? Just for us, let's do SN2, just for now. Okay, so what should we do first?
Protonate the alcohol.
Because it's a bad leaving group, we have to make that into a good leaving group. Protonated becomes a good leaving group. And then do what? You can do SN1 also because that's benzylic, it's a stable carbocation, but we are choosing to do SN2. What were you saying, Mark?
BR.
BR minus.
Reason that one goes more than the other, I suppose, heat,
Say that again, please.
is what promotes one over the other?
One meaning SN1, SN2? Neither.
Neither?
Neither. There's no way to control unless your substrate is one that stabilizes a carbocation or doesn't stabilize the carbocation. Heat is not going to affect one or the other. And then of course, please, if it's SN2, make sure you're showing the transition state. Every single time when that goes through, that becomes benzyl bromide, and of course, water is the side product. But the point I want you to notice is, this is exactly the same mechanisms that we've done for SN1, SN2. Protonate, you got a good leaving group, then nucleophile can come in, kick out the leaving group, SN1, SN2, depends on whether the substrate is primary or secondary or so on and so forth. Make sense, everyone?
Mm-hmm.
Questions? Okay, so try this one then, and please tell me what would the product be, and you can write the mechanism at home. Products, products. So what if it were products? Quick.
Phenyl iodide.
Are you sure?
Yeah, I don't think.
Pause. Don't be that quick. Remember, it's substitution reaction, SN1 or SN2. So you also have to keep that in mind. Anybody? Can both sides do substitution?
No, are you just gonna get butyl iodide?
Can both sides do substitution? I heard no from one person. Let me hear from more. If you're here, let's do this.
It's
Can both sides do a substitution?
No.
only one side.
Which
can-
side cannot do substitution?
The
Why?
because it's vinylic.
The phenyl, not vinylic. Vinylic is for an alkene.
Oh.
This is phenyl. sp2 hybridized carbon. Cannot do
sp2.
SN1 or SN2 on sp2 hybridized carbon. So can this bond break?
No.
No. That bond cannot break because that carbon cannot do substitution. Can this side do substitution?
Yes.
Yes.
SN1 or SN2?
SN1.
So what are the products? So this you can't break because that cannot do SN1 or SN2. So what does this become?
T-butyl iodide. Phenol plus.
That can't break. Agreed? Everybody okay?
Mm-hmm.
And what does a T-butyl group become?
T-butyl iodide.
And it can't go any further. It stops right. Please write a mechanism for this to make sure you understand why. And yeah, and let me know if you have questions tomorrow. Everybody okay? And that's kind of it for ethers. There's really not much ethers can do except break apart under if you have HX around. Okay, there is another kind of ether that you've seen before. It's really an ether if you think about it.
Epoxides.
Does that ring a bell? Epoxides?
Yes.
What's an epoxide?
An epoxide is a triangular ring that has an oxygen.
So 3-membered ring structure.
With a charge?
There's no charge.
Not a charge.
Can't have charge because oxygen has 2 bonds.
Oh, yeah.
That's an epoxide.
Oh, that's when the Cl is. I know.
Yes, that's in the mechanism of halogenation of an alkene.
Yeah, sorry.
Do you guys remember epoxide?
Yes.
Mm-hmm.
What do we make epoxides from?
Br.
We
Two.
we use an alkene
An alkene.
and we react it with MCPBA.
Okay, so I'm going to choose a specific example.
Wait.
So let's say we have 1-methyl cyclopentene. Absolutely, MCPBA, which is a per acid, creates an epoxide. Everybody agrees?
Yes.
And of course, you'll get epoxide being on the top or at the bottom. You get both of them. Does that ring a bell,
Yes.
everybody? Okay, there is one other way of making an epoxide. Can you tell me what will be the outcome of this reaction? Because we've learned this before. What will this reaction produce?
OH and a halo.
But which is where, what is where?
The top one would be.
It's a halohydrin.
Halohydrin.
Halohydrin, and where will be the OH and where will be Br?
Oh wait.
So methyl and then the OH on the top. No, wait.
So we need to know mechanism for that.
Yeah, it should
And-
go to the most substituted.
The nucleophile goes to the more substituted
Mhm,
once you get the halonium ion. So please, mechanism you got to know for this one. We've talked about it. But here's the big question. What is the relative orientation of the Br and OH?
Anti-curve.
They have to be anti. Do you guys agree?
Yep.
Does that ring a bell, everybody?
Yes.
Mm-hmm.
So let's say if this is a wedge, of course, then that would have to be a dash, but then this will have to be a what?
dash.
And of course, you'll get the other version as well. Agreed?
Mm-hmm.
Do you all remember that reaction? We spent quite a bit of time on that.
Yes.
Okay. Once you get the halohydrin can be deprotonated by using sodium hydroxide. What do you think that will do? Come on guys, is that an acid, a base, an oxidizing agent, reducing agent, what?
It's a base.
What does the base do?
It accepts protons.
And where is the proton coming from?
The OH group.
Right? If OH loses a proton, what does it become?
And
And what is O minus going to do?
it'll want to make a second bond.
Well, okay, fine, let's be more specific than that.
Alcox.
So if O minus is here and Br is on a dash, what is it going to behave as? If is it electron rich, electron poor?
Electron rich.
What do electron rich things want to react as?
No,
Electron rich things will either react as a
electrify.
A
base or a
base or
nucleophile. Nucleophile. Can it act as a nucleophile? Is there a leaving group?
Yep.
Absolutely. An intramolecular SN2. Within itself, SN2 right there. And look, they're also situated in the exact way you want, because SN2 means the nucleophile has to come from the opposite side of the leaving group. And yep, that's on a wedge, this is on a dash. They're already opposite, so this one can lean in and pick out the leaving group. What's the outcome? When that happens, what does it make? An epoxide. Of course, in this example, the epoxide will be on a wedge because it came from the top side, so it picks out the leaving group. That's also one of the ways in which epoxides have been made, is first make a halohydrin and then deprotonate the alcohol, which then makes the epoxide. Everybody sees that? Reactions, oh, sorry.
If they weren't opposite, this wouldn't happen.
Say that one more time.
If they weren't opposite, this would not happen.
No, it can't, because you need that, which fortunately will always be. Because the mechanism of this reaction is such that they will always be opposite. So it works out. But if they weren't, then you can't. Absolutely. Everybody okay? Yes? Okay, reactions of epoxides. We've already done all of them actually. So why don't I just write a question so we can review what we've learned before. Is it okay if I use this as an example?
Yes.
Sure.
So the only reactions of epoxides that we need to know, we've already covered them in a different chapter, which is ring opening of the epoxide. The ring actually snaps open, and it can either be under acidic conditions or basic conditions. Your job is to remember under which conditions does the nucleophile go here or go there, depending on what's being used. So please, we've covered all of these reactions, so please go ahead. If the epoxide ring opens under non-acidic conditions, where does the nucleophile go?
Least substituted?
When the epoxide ring opens under acidic conditions, where does the nucleophile go?
The substituted?
And opposite side. So you also have to keep that stereochemistry in mind. Remember that, guys?
Mm-hmm.
Please go ahead. Tell me what would be the outcome for each of those. And you should be able to write mechanisms for all of these. But for now, just give me the products. Please feel free to go on the board, write your answers, please.
Yeah.
Not seeing any answers up there, guys. Come on. Perfect. That's under basic conditions, so nucleophile went to the less substituted carbon and opened up the epoxide ring. The opposite for that, and notice their relative stereochemistries. It has to be from opposite sides, so they will always be anti. Good. Okay, so let's pause there. Which step is the ring opening in? Is it opening in step 1 or 2? If you think about the mechanism happening, is the oxygen getting protonated first before the nucleophile attacks, or is the nucleophile attacking first? So is the oxygen protonated?
No.
So where would the nucleophile go? Will it go to the less substituted or the more substituted? So you got to think about, okay, which step is the ring being kicked open? If the ring is being kicked open with the acid around, which means the oxygen is protonated, then the nucleophile will go to the more substituted, like you did. But if the ring is being opened without the oxygen being protonated, then the nucleophile goes to the less substituted. Yes, exactly. Exactly, that would be a product. Yes, not the other one. Does that make sense?
Mm-hmm.
So you're thinking about the sequence of events. In this particular case, for example, when they're both together. Please understand the difference between this and this. They're totally different things. So here, the two are together, which means the acid is going to protonate, and then the nucleophile will attack and open up the epoxide ring. So in that case, the nucleophile goes to to the more substituted carbon. But here the situation is different. The nucleophile is right there. There is no acid in here, right?
Yep.
If there's no acid in there, is the new oxygen going to be protonated?
No.
So where would the nucleophile go? It will
Least
go to the less
substituted
substituted,
carbon.
open up, and then that protonates the O minus. So it's all about that sequence of events. Absolutely, you're absolutely right. Nobody else is?
H3O plus and OH.
Anybody else? Are you okay to go?
I have to hold this and use
So
carbon.
let somebody, why don't you just?
I can help him.
Yeah,
I mean, I can help him hold
She can see
it.
your answer and write it.
All right,
Yeah,
okay.
absolutely.
Okay.
What about sodium borohydride and lithium aluminum hydride? Oh, you meant that way, yeah. Anybody? Nobody? Come on, guys. I love the level of enthusiasm in this room right now. It's week 10, right? Wait till week 10 next quarter. Come on, what about LAH and sodium borohydride? You were just getting ready to go, Vincent. What happened? You got it?
No, I was working on the mechanism for
Okay, so what's the
I think I
new
have the answer, but
so
in sodium borohydride and aluminum hydride? What's the new?
I didn't do that one. I don't like because I have to log in.
That's okay. That's okay. That's fine. That's okay. You did. Is that an 8? What is that? This right here. Oh, you're still writing.
I'm sorry.
Okay, then let me not bother you. No, that's good.
Yep. Thank you, Mom.
So, okay, so, well, in this case, yeah, actually it doesn't matter, right, except stereochemistry because they're both going to be OHs, but yeah, absolutely right, Carter. Yes, yes. Yes, so what's the nucleophile with lithium aluminum hydride and sodium borohydride? What's the nucleophile that they provide us with? H
Hydride.
minus. And where would it go? To the less substituted or more substituted?
Less.
Because there's no acid, exactly. The only thing I would suggest is, your answer is absolutely right. The only thing I would suggest is don't just show one hydrogen when there's supposed to be two. Either show both or don't show either.
Okay.
Because otherwise it confuses that, is that just one, or, but then you didn't put a charge, so.
And this will just be the opposite of the.
No, it'll be exactly the same thing.
Oh,
They do exactly the same thing. You'll
Okay.
get the same product too, because again, the nucleophile is H minus, but there's no acid. So the nucleophile goes to the less substituted carbon and kick out the epoxide.
Makes sense.
Yeah, same product by both of them. Does everybody remember doing this? Please write every mechanism, understand why, how, so that you get fluent with it. You should be able to write all of these mechanisms. Anyways, how? So why don't we stop here? Brainstorm. Think about it. First thing tomorrow when we meet, you're going to tell me how. Maybe even write it on the board at the start so we can see, okay, how do we create that product? You can use this alcohol and you can also use toluene and acetylene to bring in more carbons if necessary, and tell me how tomorrow. Tomorrow we are not having lab, isn't that right?
Yeah.
But we are having a lab quiz, because remember a lab quiz that we skipped because we weren't ready to do it last Tuesday. But I think now we are way ready to do it. So is that correct? Mm-hmm. Yeah. So lab quiz on we'll do that first, and then I think we can actually cover substantial material tomorrow. For the remaining 2 chapters tomorrow.
So it's a lab quiz on the
lab we did last week.
on
the Grignard lab.
Grignard.
Yes. Yes. Yes.
Or a lot of notebooks tomorrow?
Yeah, that's a good question.
I did
What do
mine
you
last.
guys want to do? You want to give them to me tomorrow?
I did
And then
mine.
I see that expression on your face.
I did mine yesterday.
That's
Wednesday?
great, Carter. Sorry, what?
We do Wednesday maybe?
We can do Wednesday.
Okay. But
Or we can do, so we have tomorrow, by the way, I still haven't found us a room. I will, and please watch out for that in the announcement. We have tomorrow, then we have Wednesday, right?
we don't have it.
We have Monday next week, but we are not going to cover new material, at least I don't want to cover new material, because we have the presentations on Monday. Isn't that right?
Yeah.
Everybody is ready for their presentations or getting close to it?
I was just wondering, did you want it in like a PowerPoint or does it not matter? Like
It's
a Word
totally
doc?
up to you.
Okay.
Totally fine. If you already have a poster board, you can just use that, but if you want to accompany that with totally up to you.
Okay, so we can like, if we just have like a PowerPoint slide, can we just put it up there?
Yes,
Yeah, okay.
absolutely. Yeah.
No quiz on Monday?
No, I don't think there's one in the schedule. Can someone confirm? I don't think there was.
Let me see.
Ooh, is it in the schedule? Could someone please check the schedule? Does it say a quiz?
Quiz 8.
No, it doesn't. Oh, I see. Do you see? I'm actually missing quiz 5 in the schedule. There's not. So I think there are only total 7. So there is no quiz scheduled for the Monday next week. So no, we won't, because our final is on Wednesday.
Wait, when is our last quiz then?
It's done.
Last quiz is.
It was today. Oh, it is today. You guys are gonna.
Oh, okay.
Okay, does that make sense? Everyone okay with that plan?
Yeah.
Now, exam is on Wednesday next week in this room at noon. Please remember our final starts at noon, not 12:20. Noon, it's when it starts. So lab notebook, what did we decide? Yes.
Wednesday or Monday?
I would prefer Monday because that will give me a couple of days to grade and give those back to you on the day of the final. So you can take them with you as opposed to me keeping them. So let's do it Monday then? Lab notebooks Monday?
Okay.
Everybody, Monday? Cool. But if yours is done, for example, and you just want to give it to me tomorrow, that's okay. Give it to me. Oh, are you
I'll
okay?
decide.
You can give it to me tomorrow. So if anybody finishes the lab write-up before Monday and you want to give it to me tomorrow or Wednesday, totally fine. Just give it to me. And then I'll return it to you. Yes.
Yes, I did my extraction on my iPad.
But I need to grade it, right? How would I grade it if it's on your iPad and not on the paper? Unless you give me your iPad.
You got to pay the price, Vaughn.
There's paper there.
Or you could
You could probably print, like, is there